In this demonstration, an introduction will be given to the FDTD solver in FEKO. We will use the FDTD to model a 4-port microstrip coupler on a finite substrate. We start with the model already set up. The model consists of a microstrip line on the top and bottom of a finite substrate. A ground plane with apertures separates the top and bottom halves of the dielectric. To view the detail inside the dielectric, we activate a cut plane. The volume display of the geometry can be disabled as shown. This allows the viewing of the bottom microstrip line, and if we zoom in, the wire connections and edge ports to the ground plane. Adjusting the cut plane height allows viewing of the ground plane and the 4 apertures in the ground plane. Adjusting the cut plane again, similar to the bottom half, we see the wire connections and edge ports for the top microstrip line. If we disable the cut plane and then view the simulation mesh, we see a triangular surface mesh. This means the model is being solved with the method of moments, a frequency domain solver. To change to the FDTD solver, go to the Solve Run tab, select Solver Settings, and on the FDTD tab, tick the box Activate the FDTD solver. We see after ticking this box that the old mesh has disappeared. This is because a new mesh must be generated for the FDTD. To view the model again, click Model View. Next, we create the new mesh. This will be a voxel mesh. Before creating the mesh, CAD FEKO shows the total number of voxels that will be created. The selectable mesh sizes in the drop-down box are explained in the user manual as shown. Note that for the treatment of fine geometric detail in the mesh, the Advanced tab of Create Mesh can be used. More detail on these settings are available in the user manual. Now we create the mesh. Click Simulation Mesh to view the mesh. The bounding box can be viewed by clicking FDTD Boundary Conditions on the Solve Run tab. Suitable defaults are chosen by CAD FEKO, and for advanced use, it is possible to modify the bounding box. For example, using a PEC boundary, an infinite PEC plane can be modeled. We inspect the mesh a bit further by activating a cut plane to view the wire connection and voxels inside the dielectric. Each voxel for the geometry can be viewed by checking the volume box in the simulation mesh group. The requested output has already been set to calculate S parameters. Note that each additional active port will require resolving the model. Lastly, before we run FEKO, it must be noted that GPU acceleration is available for the FDTD. This can be activated on the FEKO tab of Component Launch Options. For this notebook computer, in this demo, a GPU was not installed. Using a GPU can speed up the solution time by a factor of at least 10 times. Now we run FEKO. FEKO indicates that the FDTD solver is used and the estimated maximum number of time steps is given. When FEKO has finished, click OK and run Post-FEKO to view the S parameters. Post-processing, a solution done with FDTD, is exactly the same as for other solvers. We create an empty Cartesian graph and add the S parameters as shown. Note that the model is available in the examples guide of the FEKO installation. This concludes the demonstration. For help in setting up your own models, please contact FEKO support.